Welcome back to another Cram video for AP Physics 1. We're still dealing with these systems of accelerating objects. Okay, and a good example here today is going to be a man accelerating in an elevator, going upwards or downwards, and calculating his apparent weight. Well, let's look at the entire system together. There would, of course, be a force applied going upwards. Okay, and then of course, we have force gravity going downwards here. Then our driving net force equation is going to then be force applied minus force gravity. Now, when force applied is greater than force gravity, we will have an acceleration going upwards. When force applied is less than force gravity, we'll have an acceleration going downwards. And we always plug in ma for acceleration, and this would then be force applied minus mg. Now, if we're looking at the entire system here, we will then plug in the total mass of all the objects here and the total mass of all the objects here as well. And we can find force applied if acceleration is given, or if we're given a force applied, we can then find acceleration. So whenever we figure that out, we can then turn our attention to the man. Now, the man, of course, would also have a force applied going upwards on him, and of course a force gravity downwards. So his equation is the same, but if we're paying attention to him only, then we're going to have his mass placed here and his mass placed here. And of course the acceleration of him will be the same as the acceleration of the whole system. So what about the two cases? Let's say force applied is greater than force gravity. Okay, therefore I would have then a positive term here, ma, okay, equals a force applied minus mg. Okay, and let's call this one the up condition. This will then get over to the other side, and then the force applied on him is then going to equal ma plus mg. Now this force applied is what's going to be pushing upwards on him, and the scale, of course, is going to be reading that force applied. Why? Because it's an action-reaction pair there. Okay, the force going upwards must be then equal and opposite going downwards then. So in other words, the force applied here would be going upwards, and it's acting on his feet at that location, acting on his whole body. And then there will be a reaction pushing downwards on the scale. So it's an action-reaction pair. And it's described here. See, weight downwards, upwards, there's a reaction pair. So there you go. So the force applied is actually measuring whatever the scale would actually be measuring at that point. Now what about downwards? Well, then we'll have mass times a negative a equals force applied minus mg. Now the force applied this time is going to be mg minus ma. So if the elevator is going downwards, the apparent weight of the person is now going to be less than what his apparent weight actually would be. And the reason is the action-reaction pair has now decreased because our force applied is now less than the weight of the person. Now what about when velocity equals constant? Well, in that case, the force applied is going to be equal to the force of gravity. So if you look up here, I would then be putting in a 0 for acceleration. This whole term here becomes 0, therefore force applied must equal the force of gravity. So that's kind of how you determine a system of objects when they're accelerating upwards or downwards in the presence of gravity. Now, of course, we have ignored any presence of friction in this situation. Now, what about a system of objects that are accelerating, okay, along a horizontal surface? And again, let's ignore friction. Let's call this one M1, okay, and we'll call this object here M2, and this one M3. And of course, we have a force applied going in this direction here. Okay, so then if there's no friction, then force net is just going to equal m times a. In this case, force net is going to be equal to, I'll put a capital M times a. Okay, okay, and then we'll set that equal to the force applied, right? Okay, so force applied, there's no friction here at all. So I'm going to have capital MA is equal to our force applied since there's no friction at all. Now what does capital M stand for? Capital M is going to equal M1 plus M2 plus M3. Okay, all of those things, added together. Okay, now what about the contact forces that exist, okay, between the objects? We're going to have a force going in this direction and then backwards. So M1 has got to place a force on M2, but then right back at you. M2 will push right back on M1. And what about the contact forces between these? M2 and then M3. M2 will apply a force to M3, and M3 will push right back at you again. So how would we calculate those? Well, the key to that is understanding that block M1 is responsible for pushing M2 and M3 at the same acceleration, okay, that is existing there. So let's call this action-reaction pair force 1, and let's call this action-reaction pair force 2. So then force 1 has to equal M2 plus M3 multiplied by the same acceleration that we've observed above here. Okay, so box M1 only has to push 2 boxes at the same acceleration. Now what about F2, force 2? Okay, force 2 is going to equal M3 times the same acceleration. Why? Because M2 only has to push box M3. Now remember, the force going this way is equal to the force coming back because of Newton's third law. And finally, this one must equal this one coming back. Now if I wanted to calculate the net forces on any one of those objects, then I can find the force net, and I can say times M1 times A. Okay, so that'd be the force net on the M1 box. If I wanted force net on box M2, I can just say M2 times A. And if I wanted the force net on box M3, I would just say M3 times A. Reminding that when I want the net force on any individual object, it's always the individual object's mass multiplied by the individual object's acceleration. And the acceleration in all of these examples is going to equal to the A that we found initially by our force applied, equals capital M times A.